I would like to invite our colleague from John from Abengoa to present and also the system of large-scale storage demonstration and to the system. So, John.
Hi, thank you, Thong. I hope that you can hear me, and I hope that you can see also my screen. Let me 1 second. I'm looking for my presentation. So, good afternoon, everybody. Can you hear me properly?
Yes. Go ahead. Yes.
Okay.
Yeah, you can put in the full screen if you want.
Yes, but it is already in the full screen. I can apply some little zoom. So good evening, everybody. My name is Juan Cabeza, and I'm from the Spanish company Abengoa, who has been the team leader of the World Package 5. And during my presentation, I'm going to provide you with a briefly recap of the project with some highlights, and afterwards I will pass to explain the activities that we have performed in order to validate the project, and I will focus on the results and the lesson learned. So here in this first screen, this is a brief description of the project. The idea, as you can see, is the development of a BESS, but not only as a mere storage system, but to play an important role in the operation of the system. This is in line with the aim of the FLEXITRANSTORE project, thus, as Nikos has explained in his presentation. This BESS is installed in the Athenios station in Cyprus, which is a very test field, a very benchmark for testing. As you can see, in the area of influence of this station, there is a large presence of photovoltaic systems. So that the impact of the renewable generation can easily be noticed, and the electric system in the area is also subject to significant variation, mainly due to the tourists in summer. The BESS, that is the object of the project, is conceived to work under these constraints to improve the reliability and the flexibility. Reliability because the performance of the BESS are intended to improve the suitability of the electric system, and to support and solve the problems that can be expected due to the high presence of the renewable sources. Flexibility because it is conceived in a way that permits its operation both on site, both on remote modes, and allows the several actors that are involved in the operation of the system to work with it. You will see this point more clearly when I really explain the communication scheme. Here, this is a briefing on the system. In the picture, you can see the container that houses the batteries and the inverter. We have used lithium-only batteries, totaling 1 megawatt of power, 2 megawatts per hour of energy, and one important point is that mostly all the components of the system are housed in the container, which helps his transportation from factory to site, his installation on site. Outside the converter, we only have the one step-up transformer to connect the system to the external grid, and the SCADA that is in a nearby building in the substation. Apart the main units the main units component the control system, as you can see in the picture, we have the front end controller and the energy management system, which are housed in the battery container. This front end and the energy management system are intended to manage the operation of the batteries, and also to control the generation, the injection or absorbing of active and reactive power to the grid. The AES SCADA is, as I have mentioned, is in a nearby building of the substation, and from it serves also to perform the same functions that the front end controller and the MSS do, but also monitor the container and the area of influence, and finally can be used to generate the dispatching of power. And the structure of the overall control system, as you can see, the control system controlling the base comprises 3 levels: front lever controller that is intended to provide to perform the voltage and frequency regulation and providing inertia. Second level controller that provides the grid services, and finally the third level controller that has the mission to generate the optimized schedule. And the general control system is complemented with a phasor measurement unit system that serves to monitorize the area of influence of the substation, and all of these elements are integrated in the communications network. In the picture, you can see this is the inside of the BESS container. When you can see the battery racks, and here at first sight you have the front end controller cabinet, the HMI, and here's the AES SCADA in the substation building. This is the overall communication network. You can please allow me to do a bit of zoom. As you can see, the BS is connected with the existing substation, but also with the actors that can intervene in the operation of the system. This way, the CTCO, for instance, can access to the BSS. Also, the BS can be controlled by the third level controller. I have mentioned before the role of the third level controller when describing the ADN, the active distribution node. This is a feature that allows the TSO of request in advance the power dispatching that is necessary, taking into account the expected conditions of the power system in the zone. here you have the grid services that the BSS can provide. With this template, the TSO can select the hours in which it is necessary that each of the services is activated and the amount of power that is required to mobilize for each of these services. This is an input to the third level controller. With which this input, the third level controller can determine which is the best, the optimized power dispatching that can be used. And in case that this power dispatching is acceptable to the TSO, this schedule is loaded in the control system of the BSS, so that it is automatically performed the following day. And finally, to end with the description of the ADN, these are some points that I would like to highlight. The first that the BSS gets to site already preassembled and thoroughly factory tested. The idea with this approach is to reduce at maximum the time that was going to be required for the installation and subsequent commissioning and starting up of the BSS. Regarding the test on factory, this obviously were not limited only to, let's call it, the power pack. Also the control algorithm was tested, in the fact, by means of the Howard in the Loop lab that was located in Loyola University facilities in Seville. Again, the idea is to test in advance the overall system to anticipate any point that could be solved prior to send the equipment to site for the installation. And finally, since most of the partners that were involved in the project were located outside of Cyprus, it was provided a continuous monitoring of the BSS in order to control the real status of the BSS and to anticipate any problem that could arise. This that you can see in the screen is a dedicated software to manage the status of the batteries. And specifically, we were interested in the SOC, in the state of charge on the batteries. This software also gave us an idea of the possible alarms that could rise in the system. Well, once the system was installed at site, several demonstration activities were performed in order to verify the work done. These activities were performed both at site immediately after the commissioning of the system, and also in remote. The site test was mainly devoted to verify that the BESS was able to inject and to absorb power to the grid, both in continuous mode and or in fast charge and discharge mode, so that we could be sure that that the BESS was successfully responding to the power setting that was sending to it. And some of services like frequency regulation or voltage regulation was also tested on site. Afterwards, we perform a set of tests in remote mode with all the partners being connected through the communication network, and you can see the check-ins that were performed successfully performed with at the different levels of the control system. In parallel, the phase of measurement units were tested, and it was possible to confront the results of the measurements of the PM units to the measurements that were done during the test, that serve us to also verify the phasor measurement system. The results, as I was advances, were that the design of the BESS was validated. The BESS is able to inject to absorb power with a good efficiency, actually greater than was initially considered. The grid services that the ADN can provide were also validated. With the close collaboration from the TSO and DSO who actually cooperated during the test, it was possible to validate the generation of the optimized schedule, and finally, as I had mentioned, the PME operation was validated. Concerning the lesson learned, the concept of the ADN is using a modular system, a modular scalable system that can be repeated and adapted to several scenarios. During the test that we have performed in this project, we had the constraint that the limit of the BESS and the BESS size was actually limited, due that it was necessary to find a balance between the performance of the BESS and the fact that this is that it was a demonstration activity. And one of the points that could be seen outside that was that although the system was working properly, further development should allow to have additional space from elements that could help to ease the access to the BESS components and facilitate the operation and maintenance. Another important point was to see that the BESS was in fact easily to operate and tested in remote mode. And regarding this, both the HA lab platform and the remote monitoring was really helpful, both during the commissioning and during the test. Finally, the recommendations. And again, we are aware that one of the research lines is to try to reduce the size of the batteries in order to enlarge the available power capacity, and I strongly recommend that the research can follow this line. And finally, to finish, I would like to highlight that this technology is mature enough to be implemented in an existing system, as we have done during the project. That the role that this technology can play in a scenario where the presence of the renewable energy is important has also been demonstrated, and we believe that it can be useful and easy to adapt to the particularities to the different national codes. Finally, to finish, I would like to thank the consortium in general, and specifically the support that we have received from our partners during the development of the project and during the commissioning and startup. We have been really well supported, especially from our local partners from Cyprus, who has actively helped us during the commissioning at site, and have actively participated during the testing specifically during the generation of the optimization schedules. So thank you all.
So thank you very much, John. Also thank you for hosting us and inviting us to this excellent, very impressive premises of Abengoa 2-3 years ago. So we just wonder if there any burning question. It's also very impressive to see that now it become very advanced with what your testing, and also the efficiency of the system is higher than expected.